Hi folks, and welcome back to Math with Captain Rod. The purpose of this video is to demonstrate how to solve equations, differential equations that are exponential in nature. The example we're looking at here is going to be an example about bacteria. And we're going to imagine here that we've got some sort of bacteria colony. And after a 3-hour time frame, the number of bacteria is 10,000 in this example. And then 2 hours later, or in other words, at t equals 5 hours, the number of bacteria is 40,000. What we're going to try to calculate is what I call n sub o here, the original number of bacteria in this colony. Now, bacteria population growth is an example of an exponential type function here, and the key to understanding this is that the rate at which the bacteria are multiplying is directly proportional to how many there are. So that allows us to start with this. dn dt has to equal some constant times t. I'm sorry, n, not t, n. Right? And this is saying that the rate that the bacteria multiply by is directly proportional to how many there are. Now, this is an example of a differential equation that's separable. It's the first derivative, so I'm going to go ahead and rewrite this. Let's see, how about dn over n equals k dt. All right, the k is some constant that probably will need to be determined in this problem somewhere. This equation is solvable by integration of both sides. Now, kind of funny looking integrals there. You can actually do this with or without limits. I'm going to go ahead and do it without limits. You know, what we could do is integrate this from n sub o to some n, and here from 0 to t, but instead I'm going to keep this an indefinite integral. Left hand side integrates to ln of n. Right hand side integrates to kt plus some constant c. Now keep in mind this right-hand side, this is the integral of k dt. There is no t here, so it's just like the integral of, say, 2x, or I'm sorry, just like the integral of, say, 2 dx, which would integrate to 2x. All right, this can be written now in exponential form, e to this power equals n. And again, this is just some constant. Now, by rules of multiplying these exponents, this can be written e to the c times e to the kt equals n. Now, e to the c, this is some constant. And you'll notice that if you put a 0 in for t, e to the 0 is 1. So this constant, this e to the c, represents the number of bacteria at t equals 0. I normally would call that something like n sub o. So I'm going to go ahead and rewrite this equation. N equals n sub o, e to a constant times t. All right. Our equation, our differential equation, is basically solved. However, we still have to determine the constants n sub o and probably k. We may be able to get the n sub o without the k, I don't know, but what we're going to do to get these constants is look at our initial conditions now. At t equals 3 hours, the number of bacteria is 10,000. So that'll allow us to write an equation here. 10,000 equals n sub o, e to a constant times t, t being 3 hours. I'll go ahead and just leave the units off. Now this equation has two unknowns. We don't know the n sub o and we don't know the k. So if you think back to first day of kindergarten, the first thing they should have told you when you walked in was, you know, nap time is at noon, milk and cookies are in the corner, and if you have two unknowns, you need to write two equations. Hopefully you remember that from way back then. So this has two equations, or two unknowns. We have to write a second equation. The second equation we can get from this second piece of information right here, that when t is 5 hours, the number of bacteria is 40,000. So I'm going to go ahead and write this. 40,000 equals, same n sub o though, the n sub o is the number of bacteria at t equals 0, right? E to the k times 5 now. So what we have now is a pair of equations here, equation 1, equation 2, that need to be solved for the n sub o and the k. Now, there's multiple ways to solve systems of equations. This one is set up really nicely to use a division to make one of the unknowns go away. Notice if we take equation 2 and divide by equation 1, over on the left we would have 40,000 over 10,000, which is 4. The n sub o's will cancel, and then we'll have e to the 5k over e to the 3k. When we take this, divide by this. And I just rearrange the 5 and the k and the 3 and the k because I think that 5k sounds better than k times 5. Now, if we take e to the 3k divided by e to the 5k divided by e to the 3k, that's e to the 2k. And that equation can be solved for k by taking the natural log of both sides. So this is now going to read natural log of 4 equals, now when we take the natural log of this side and apply the rule that log of something to a power, the power can come out in front, we end up with 2k times the natural log of e, which is 1. So k is equal to ln 4 divided by 2. I'm going to have somebody in the audience here give me a numerical value for that. 0.69, thank you. So we get 0.69. All right, now that we have this value for k, we can update our solution here. So n is equal to n sub o e to the 0.69t. All right, now we want to find the n sub o here. Again, I'm going to go back and I can actually use either of these 2 points to solve this. I know that when t is 3, n is equal to 10,000. So I'm going to go ahead and use that point. So we're going to have 10,000 equals n sub o e to the 0.69 times t, which is 3 hours. Now the other thing I could have done is used the second point, 5 hours and 40,000. This would be a 40,000, and here would go 5 hours. I'm going to go ahead and have one of my helpers here give me this value right here. Would somebody please give me e to the 0.69 times 3? 7.92. Thank you. So this is times 7.92. And then would somebody please take 10,000 and divide by 7.92? Oh, let's just round that to approximately 1260. All right, and that should represent the initial amount of bacteria in that sample. So again, important parts of this problem. One, recognizing this, that the fundamental relationship that we need to start with is that the rate in which that bacteria are going to multiply by, that rate is directly proportional to n, how many there are. 2, that yields a separable differential equation, right? And you solve it by separating the n's and the t's. So this equation here, nothing but n's on the left, nothing but t's on the right. 3, some algebra and rules about exponentials get us to here. And then 4, we apply the conditions given the problem. We know that when t is equal to 3, n is equal to 10,000. We know that when t is 5, n is 40,000. We apply those values. That yields these 2 equations, which can be solved for both k and n. Hope that example helps. Have a great day.